Section 1 Introduction. We're here to talk about large language models, LLMs, which have shown an impressive ability to adapt to new tasks and languages. The most exciting part is that these models start to exhibit advanced capabilities, like logical reasoning, only when they reach a certain size, often involving hundreds of billions of parameters. These models can generate high-quality responses without any task-specific tuning, but further tuning can be quite costly. This has led to a focus on in-context learning, ICL, where a few task-specific examples and instructions are fed into the model's input. While fine-tuning a model with task data can often lead to better performance, there's been less focus on fine-tuning models for tasks with limited data. This is likely due to the time and computational costs associated with tuning a large model, which often leads practitioners to opt for smaller models, thereby missing out on the advanced capabilities of larger models. ICL and model fine-tuning each have their pros and cons. ICL doesn't require any training cost and allows us to use the most capable LLMs. However, it often requires very large models to work well and can't take advantage of additional training examples if they don't fit into the context window. This can lead to ignoring a lot of potentially useful training examples. Fine-tuning, on the other hand, isn't constrained by the need to fit training examples into the model's input and can be quite effective even with smaller language models. These trade-offs often lead practitioners to choose one approach over the other or run costly experiments to determine the best approach. We believe that these two learning paradigms can actually complement each other. To demonstrate this, we propose Fiat, fusing learning paradigms with instruction-accelerated tuning. Fiat combines both ICL on very large models and parameter tuning on moderately sized LLMs, bringing together the best techniques from each paradigm. Fiat uses carefully crafted instruction prompts to elicit chain-of-thought reasoning from a large model, while also using the generated reasoning and instruction prompts to tune a moderately sized LLM in a parameter-efficient way. In the rest of this article, we'll delve deeper into the connections between ICL and fine-tuning, and the various techniques that have developed within each paradigm. We'll also present experiments showing how Fiat improves over both learning paradigms in data scenarios ranging from 100 to 10,000 examples. Let's start by reviewing two popular learning paradigms for LLMs, ICL and parameter tuning. We'll consider their strengths and weaknesses, which directly lead to the development of Fiat. In context learning, ICL keeps the parameters of the LLM fixed and selects an instruction prompt to improve the accuracy of the downstream task. A model prediction is made by sampling a very large pre-trained LLM parameterized by fixed theta and a textual instruction. While the instructions are prefixed onto the model input in practice, we intentionally notate them as an argument of the model, which we argue better reflects how they are conceptualized. Chain-of-thought reasoning takes ICL a step further by crafting instructions to induce step-by-step reasoning in the output of the model that improves the model's ability to arrive at a correct prediction. This allows the model to output observations about the input or solve subproblems of the overall task that future decoding steps can leverage when predicting the final answer. Few-shot ICL differs from instructed ICL in that its instructions are composed of a small number of examples selected among training examples that have been formatted as a textual input to the model via instructions. Instruction-tuned models such as FLAN and T0 often provide significant improvements on ICL compared to using a pre-trained model. This is because instruction tuning is essentially a second-stage pre-training using a set of multitask data whose distribution is closer to the downstream task. The ICL paradigm achieves competitive results on various tasks with no or only a handful of annotated examples. While it does not incur any additional model tuning cost, ICL often has high inference cost because it requires LLMs over a certain size to work well, especially when using techniques such as chain of thought. It also cannot take advantage of additional task data beyond what fits into the context window of the model. Section Summary. Large language models, LLMs, have impressive generalization abilities, but their most exciting capabilities, such as logical reasoning, often require models with hundreds of billions of parameters. In context learning, ICL and fine-tuning are two paradigms used to improve LLM performance, but they have their own trade-offs. To address this, we propose Fiat, which combines the strengths of both paradigms by using instruction prompts to elicit chain-of-thought reasoning from a large model and then using that reasoning to tune a moderately sized LLM. Section Full parameter fine-tuning. Let's delve into the concept of full parameter fine-tuning. Imagine we have a pre-trained language model, and we want to fine-tune its parameters, denoted as theta. The standard approach is to optimize all the model's parameters using task-specific training data. This process is similar to how humans engineer prompts in instructed codex learning, ICL. Fine-tuning is particularly effective when there's a decent amount of training data available. It's also beneficial for smaller language models with ample training data, as it leads to quicker results. However, it does have its drawbacks. It requires access to model parameters, which isn't always possible, and it can lead to overfitting, especially when the data is limited. To address these issues, we introduce parameter-efficient fine-tuning, PEFT. This method uses a different set of parameters, theta PEFT, which is smaller than theta. This not only reduces the risk of overfitting but also prevents the model from forgetting useful features. Like ICL, PEFT only modifies the input to the model while keeping the parameters fixed. Next, we introduce Fiat, a learning paradigm that combines the strengths of ICL and fine-tuning. Fiat aims to follow human-engineered instructions, produce intermediate text that guides the model towards correct predictions, refine its internal representation using a moderate to large number of training examples, and provide high-quality models that can handle data scales from 100 to 1000 of examples. To achieve this, we use a two-model approach. The first model, beta, is a large model responsible for chain-of-thought inference. The second model, tau, is a tunable model that learns how to best use the predictions from the beta model. The parameters of the beta model remain fixed, as we don't need any directly supervised data for its subtask. We also use instructions to improve the performance of the models. For the beta model, we use instructions to generate reasoning and explanations. For the tau model, we use instructions to align the task's inputs with the distribution seen during pre-training, which helps the model converge faster and make fewer parameter updates, reducing the risk of catastrophic forgetting. In Fiat, instructions serve a purpose similar to a Bayesian prior in earlier statistical learning methods. They allow us to encode human knowledge into the learning procedure alongside supervised data that empirically estimates parameters. However, textual instructions are a more natural way of doing this than the hyperparameters of a Dirichlet. We also use instruction-tuned models as the standard for ICL. In Fiat, we depart from the common practice of fine-tuning starting from models pre-trained primarily on span corruption objectives and instead initialize with instruction-tuned checkpoint. This makes optimization easier since the model is already expecting instructions, which can be particularly beneficial in limited training data scenarios. Finally, we hypothesize that parameter-efficient tuning is a good fit for optimizing the tau model in Fiat over the training data, because large changes to the model parameters should not be necessary given a good initialization. In Fiat, we use LoRa to parameterize the tuning procedure because it does not induce additional inference cost. Future work should consider other methods such as soft prompt tuning. This brings us to the final formulation of Fiat used for fine-tuning and inference. Section Summary. Full parameter fine-tuning optimizes all parameters of a language model on task-specific supervised training data, but it can lead to overfitting and requires access to model parameters. Parameter-efficient fine-tuning, PEFT, reduces overfitting by using a learning parameterization that avoids forgetting useful features. Fiat combines the strengths of instruction-based continual learning, ICL, and fine-tuning, allowing the model to follow instructions, reason through intermediate text, refine its internal representation, and scale with different amounts of training data. It achieves this by fusing a big model with powerful capabilities and a tunable model, using instructions to guide the learning process. Section: Datasets. In our research, we aim to use a wide range of datasets to test our models. These datasets were chosen to cover a variety of tasks, from classification to short answer generation, and to include a diverse set of languages. This was done to evaluate the versatility of our method. Our first dataset, XOR-ATRI-QA, is a classification task where the model predicts if the given answer to a question is supported by the provided context. This dataset includes 5 languages and a total of 262 examples. We refer to this as a scenario with around 100 data points. Next, we studied the behavior of our model, Fiat, on the cross-lingual QA task of Extreme Up. This task is an extension of the XOR QA dataset, which is a cross-lingual version of the Tidy QA dataset. Here, the model is asked to predict the correct English answer given a non-English question and an English answer passage. This task is particularly important for languages with limited answer content, as it allows for answers to questions that would otherwise be unanswerable using only in-language content. We focused on two subsets of this task. First, we used a subset of 20 Indic languages where each language has about 300 examples. This allowed us to study a scenario with moderate data, which we refer to as a scenario with around 1,000 data points. We also studied the full Extreme-up cross-lingual QA task, which includes 22,500 examples across 27 languages. In this case, the 5 languages with the most resources each have more than 2,500 examples. We refer to this as a scenario with around 10,000 data points. For our models, we used POM2 as our base model and experimented with instruction-tuned models using the Flan mixture. We compared our models to both ICL and fine-tuning baselines. For ICL, we used POM2L with chain-of-thought reasoning. However, for the Extreme-up cross-lingual QA task, it was not feasible to hand-engineer prompts for each of the 27 languages. Therefore, we wrote 4 chain-of-thought explanations based on Bengali exemplars and used the same ICL examples for all 20 languages. Our results showed that the Fiat framework outperformed the baselines in all 3 data settings. We found that the best baseline varied between ICL and fine-tuning across different tasks and data size settings, making it difficult to determine the best approach without empirical comparisons. However, Fiat consistently offered the best performance by combining the strengths of both ICL and fine-tuning. In our analysis, we found that instruction-tuned base models improved the final quality of fine-tuned models. The instruction-tuned Flan XS model performed better than the base model on all datasets, especially on XOR QA and Extreme-up cross-lingual QA Indic, where the total amount of task data was around 100 to 1000. This suggests that instruction-tuned models are beneficial not only for ICL but also for fine-tuning on limited data. However, the advantage of instruction-tuned models decreased when the fine-tuning dataset was large. Section Summary. The section discusses the datasets used in the study, including a classification task called XOR QA and a cross-lingual question-answering task called Extreme-up. The authors compare their Fiat framework to baselines and find that Fiat outperforms both few-shot ICL and fine-tuning methods. They also analyze the effect of individual design choices within Fiat and find that instruction-tuned models improve the performance, especially on datasets with limited training examples. Section. Instruction-augmented tuning generally leads to significant improvements. We found that enhancing the tuning process with specific instructions can significantly improve the performance of our models. This is particularly beneficial for all tasks, and not just for few-shot instruction following tasks. This suggests that the art of crafting prompts is not only useful for direct few-shot instruction following tasks, but it also positively influences the fine-tuning of the model. This method of tuning with prompts is especially beneficial for tasks like XOR QA and Extreme-up cross-lingual QA Indic, where there's a scarcity of task data. The reason for this is that the prompt format brings the task closer to the model's pre-training distribution, allowing the pre-trained model to generalize to the task even with a limited number of examples. We've also found that our method of tuning, which we call COT-augmented tuning, is beneficial for most tasks. It can lead to significant improvements, especially for the Extreme-up cross-lingual QA Indic task. Interestingly, it doesn't seem to help with the XOR QA task, which contradicts previous findings that explanations can be particularly useful for classification tasks. We think this might be because the model already performs quite well on the XOR QA task without needing the explanations, and this task might be reaching its peak performance. We've also noticed that COT-augmented tuning is even more beneficial for tasks and languages that initially perform poorly. We've analyzed the relationship between the improvements brought by COT-augmented tuning on the Extreme-up cross-lingual QA tasks. We found that there's an inverse relationship between the benefits of COT-augmented tuning and the baseline model score. This suggests that COT is more beneficial for more challenging tasks or languages where the model struggles without the help of COT augmentation. Recent work has proposed a method called distilled COT, which uses the explanation as a multitask output target, so the model doesn't need to generate additional explanations during testing. When we compared the performance of these two different ways of using CAUT explanations, we found that despite having a higher inference cost, our CAUT augmentation method outperforms the distilled CAUT by a significant margin on the more challenging extreme-up cross-lingual QA indic task. Adding instructions to the tuning process helps from the very beginning. We've plotted the training curves of the Flan PaLM 2S model with and without instruction-augmented tuning and found that adding instructions to tuning leads to much better performance right from the start, before any model optimization. This suggests that adding instructions to the task data during fine-tuning can significantly improve the model's initial performance. We've also found that instruction-augmented tuning is more beneficial when used with an instruction-tuned base model. We compared the effect of prompted tuning on models with and without instruction tuning and found that prompted tuning generally improves both types of models. However, the improvements on the instruction-tuned Flan model tend to be slightly larger and more consistent. Instruction-tuned models often perform better for few-shot instruction following tasks than base language models because they're already primed to follow instructions due to being fine-tuned on a diverse set of tasks. Using instruction-tuned models is a key component of our approach. In-context learning, the parameters of the language model remain fixed and a prompt containing a few examples along with reasoning steps is used to prime the model for solving similar tasks. This method works best for large language models. We use this capability of large language models, along with fine-tuning, to power small language models in situations where there's limited data. Section summary. Instruction-augmented tuning generally leads to significant improvements in various tasks, indicating that prompt engineering is beneficial for both direct few-shot ICL and model fine-tuning. CAUT-augmented tuning is especially helpful for tasks and languages with lower performance, and it outperforms CAUT distillation, showing that adding instructions to tuning improves zero-shot performance and reduces the risk of catastrophic forgetting. Section. Knowledge transfer from larger to smaller LLMs. Transferring knowledge from big to small language models. A common technique for sharing knowledge from larger models to smaller ones is model distillation. This involves using the outputs of a larger model as a learning guide for a smaller one. Another strategy involves the larger language model creating data, which is then used to train smaller models. This method has recently been expanded to include the generation of reasoning steps, which are then used as fine-tuning data for the smaller language model. Languages with limited resources. Most research that trains large language models and applies them to specific tasks focuses on English or about 100 other languages with abundant, readily accessible corpora. Languages with limited resources, often referred to as tail languages, have typically been overlooked by language technologies due to the scarcity of available corpora. However, recent research has begun to pay attention to these tail languages, moving away from the more commonly studied languages. In our work, we concentrate on the low data scenario, which is particularly beneficial for these tail languages. Refining smaller language models. While refining with prompts has been explored for encoders pre-trained with masked language modeling objectives, we demonstrate that it's also crucial to fine-tune generative language models. For instance, some studies suggest that refining a smaller language model is a more competitive and efficient approach for practical low-data learning problems than the few-shot ICL method. We propose using synthetic QA data, generated from very large language models, to enhance the performance of a smaller model.